Hi, everybody. Welcome back. Today, we're going to wrap up our unit on lumped capacitance. What I want to do is to spend the whole class today looking into one concrete example that I think many of you can relate, and I think it's a pretty cool example that is thermal balance in microprocessors. And we're going to look into times and temperatures in microprocessors, powers, and we're going to also investigate the case of a failure of the fan and its consequences. So before we get into that, let's take a quick review of what we have seen so far. The quiz on Wednesday next week is going to cover everything until the end of the class today. Okay, so these are the notes that you have uploaded, and I want to look at lumped capacitance from a point of view of one, understanding what it is, two, having an intuitive feel of what it is, and three, putting the math to reproduce the same intuition we had, but this time with added numbers. So number one about what lumped capacitance is a system in which everything inside the control volume is at the same temperature. Sometimes it happens, sometimes it doesn't happen. But we're going to determine when next week. Today, we're going to assume it happens, and we're only going to look at cases in which the temperature inside the control volume can be assumed to be more or less constant in space. Now, is this constant temperature, which is constant in space, is it constant in time? No, that's the whole point. We're going to analyze now how the temperature in a system changes with time, right? Without needing to worry about how it changes in space due to gradients and conduction. So of all the heat transfer mechanisms we have seen so far, radiation, convection, contact are all mechanisms that happen through an outer surface, the AS. Conduction, which we also studied, is something that happens inside through a cross-sectional area, AC. So if it is, because conduction is driven by gradients of temperature inside the control volume, if I say that the temperature inside the control volume is constant, that means there are no gradients. That means there is no heat conduction, and that means we're very happy. We don't need to wear with difficult equations. Now, the whole problem gets reduced to a balance of energy between the exchange of surface energy through the surfaces and whatever might be generated or stored inside the control volume. So we looked at an example of a copper sphere and some things that we typically know in lumped capacitance problems. Number one, we typically know the starting temperature. And if we don't, now that we know the equations, we could solve for it. But let's say in this case of the copper sphere, we know it. Then we know also, and it doesn't need to be a sphere. The example of the copper sphere is so I can put numbers that are easy, but it can be many other things. So we know the starting temperature. If this body of whatever shape it has is immersed in a fluid, whatever fluid it is, after enough time, if there is no heat generation, the final temperature is going to be that of the fluid. In a couple of minutes, we're going to discuss microprocessors in which there is heat generation, and it's a different story with the same equations. But just refreshing. So we know in lumped capacitance, without heat generation, where at what temperature we start, we know at what temperature we finish. We brought up the concept of characteristic time in order to give a number to a curve that doesn't have any sharp point to which attach a characteristic point. And we said characteristic time, and we'll down the road when we study the physics of convection, we're gonna see we have characteristic distances too. And when we studied heat exchangers, we're going to study characteristic length of entry and those things. And we're always going to use the same concept, that is, let's take a tangent at the start of the curve, and let's extrapolate that tangent until it crosses the line of the steady state. Where these two curves cross, the tangent at the start and the tangent for the steady state, that's what is going to determine our characteristic time. So now we can look at the heat losses, and we decided to look at losses by convection. We look at the energy stored, and all these things we learned in week 1 for heat stored and week 2 for the heat transfer mechanisms. We put them together and we end up with an equation. Okay, let me go. We end up with an equation that is a differential equation. And in lumped capacitance of a single body, which is those we're going to be looking at, the equation is a first order equation. And if we use convection, or if we approximate radiation as if it was convection, the equation, it becomes a linear equation. It's first order, linear, and it typically is non-homogeneous. It has a little term sticking out here that is a constant, which we can solve very easily with this change of variable, right? T minus, in this case, the temperature of the steady state. In this case, is temperature of the fluid. And this group here is what came from this, calling all this group in the equation, calling it K. So we got this differential equation. Whether you like it or not, and whether you think is simple to solve or not, I can tell you for sure, there is nothing simpler, nothing simpler. And it gives us the all too well-known exponential decay. That is this expression here in equation 32. This is the exponential decay, and if the temperature is, the fluid was at a higher temperature than the body, then the body would heat up also with some sort of exponential decay, but going up. We discussed briefly how to deal with radiation, and although I didn't discuss in detail in the class, you have in your notes that this is the equivalent convection coefficient for radiation. Actually works quite well, especially when the difference between the surroundings and the starting temperature is not too big. And we looked on Wednesday an example of snowmaking, and how at Snow Valley, when they don't have snow, they blow these fans that have also spray jets blowing water into the stream of the fan. And we saw how the droplet it cools down in 2 stages. First stage, it cools down from the initial temperature in which is a liquid, that I assume 6 degrees, to 0 degrees. And that happened very fast, of the order of half a second. And how then, as the droplet keeps flying, it stays at 0 degrees while it's changing the balance between water and ice. And it's getting more and more and more ice as the droplet loses heat to the environment. But because we have a phase change, it's losing heat, but it's not changing temperature. It's just changing phase, not changing temperature. And we did the calculation that it takes quite a lot of time. It was of the order of what was that, 6 seconds or 7 seconds, almost 7 seconds for the droplet, once we start to nucleate the first ice crystal, to freeze the last molecules of water into the form of ice. And what we saw is in these two stages, the first stage, there is no phase change, and we could use the equations we knew. You can use the equations outright, you can derive them. What matters to me is that you understand what's going on. In the second stage, when it's changing phase, we write the same energy balance, but now the equation for heat storage changes because it's an equation in which we don't have changes in temperature. And this is as far as we went last class. Well, we also discussed lumped capacitance with multiple elements, like for example, your car engine cooling down after you park. I want to make one curve that I think matters much, going back to the cooling of the droplets. And the cooling of the droplets was, let's see. Okay, so I'm going to do a curve of the vertical axis. This is temperature, and this is time. And I would like you to follow how I make the curve based on the things I know, right? And you'll see that the curve builds by itself, and this curve is not so intuitively. I hope you start thinking right now, as I do the curve, what do you think the curve is going to look like? All right, so what things we know? We know that the droplet started at starting temperature 6 degrees C. We know that the outer temperature was T infinity equals minus 20 degrees C. We know those things. We also know we're going to have a phase change at 0 degrees C. All right, now I'm going to make the curve what the curve would look like. So this is a lot more fun to do all together in the class. This is one of the things, these interactions that I hope we would have. It's one of the things we lose now with online learning, but at least we're healthy without COVID, at least many of us, hopefully. Okay, so we start at this temperature. Time 0, the droplet comes out of the fan, starts to cool down. Now, the droplet would believe is cooling down like this. The droplet would like that. Oops. However, as the droplet starts to cool down, trying to reach a steady state at minus 20, hits here, starts to freeze. And guess what? When it starts to freeze, it's not going to cool down anymore. So all this curve I drew here is not really going to happen. Right? What in reality happens is because, by the way, this time here, there was about more or less, I think it was 0.6 seconds or 0.5 seconds, something like that. And then it stays at the same temperature. This was stage 1, and this is stage 2. And after it's completely solid, then it's going to cool down again with whatever slope it would have, as if this was a T0, would go down. Would go down like this. This other time, here, this was more or less 7 seconds that we saw. And the question we had in the problem was, what is this time here? So, okay. I see in the chat like these type of things. Okay, good. Back to normal. So this is a problem of freezing. I have the whole rest of the day today in class, and then the office hours after class today. If this type of curve is essential, you master. You will be unable to make the curve in the quiz. You will be making other similar curves on the assignments. But for the quiz, what I care is that you would recognize what important points you have, like how the curve is starting to cool down. What was the slope of this cooling down? What happens when it starts reaching phase change? What happens after the phase change is completed? What are these times associated with them? You realize we have gone deep. We know so much. We can do so much, and all based on simple formulas. But we wouldn't be fooled by the simple arithmetic of those formulas, because there's so much conceptual content in them. All right. So this is where we, as far as we went as of Wednesday. So what I want to discuss now is the case of cooling down of a computer chip. So those of you who are into gaming often overclock the chip of your computer, or try to use special cooling systems. Some of you might even be trying liquid cooling, Peltier cooling, all kind of things, right? And I'm not going to get deep into the electronics. Funny enough, Maddie and Meki and Petroleum and Chemis all have heat transfer, but EE don't. Still, they live and die by heat transfer. Funny, huh? So let's go back to here, the class material. So this is where we were with as of last class. And let's talk about lumped capacitance with heat generation. And let's use an example. The theory you already know. Draw a control volume, do an energy balance, use the heat transfer mechanisms to replace the elements of the energy balance, look at the heat stored, and then you end up with an equation. You solve the equation and you know everything about that problem. You're golden. Let's see. Now, if we have a microprocessor, right? And this information is real information, and it's information for Pentium chips. Probably you were not even being born when the Pentium chips were out there, but I used to have one. And in these Pentium chips, right, we have a table that is a real table from Intel showing like how at different clock speeds. Look at these clock speeds. Don't they make you laugh? I remember when they cracked 100 megahertz was awesome. I had a 75 megahertz Pentium. So for different clock speeds, we have different powers. And I'm sure we can find those for modern chips, but this is what I have now. Now, you cool them down. Cooling down chips now is much more sophisticated, but way back then, you would have a heat sink made out of pins, such as these ones you see here, and you blow a fan over them. And this fan creates forces, a fluid velocity. Therefore, we have forced convection through these pins. And because there are many pins, you have a significant amount of surface area, and that is how you lose heat. And here you have, like, I put all these real numbers for the cooling of a chip of this vintage. So I want to study two things. I want to study what happens when everything goes right, and what happens when the fan breaks down. And to study these things, I want to see what are the temperatures associated with them, and what are the times associated with reaching these temperatures. We can do it. So let's start. We don't have it here, but I'm going to do. We have our obvious heat energy balance, but is missing the control volume, which I'm going to do right now. Jeez. Oh. Dang. Okay, there we go. So let's say, seen from this side, this is our chip. And this squiggly line means millions upon millions of transistors, because even the Pentium had lots of transistors. And on top of the microprocessor, we have this heat sink full of pins. This is our heat sink. Our control volume is going to be whatever is surrounding the chip and its heat sink. All right, so surrounding the chip and the heat sink. And we're gonna have some amount of heat being generated in the chip. And that's the key point of this whole problem. Q generated. We're going to have some heat loss by convection. And let's say we don't have any Q in, because the chip is, as we all know, as it runs, it gets hotter. So we're gonna say no Q in. And the balance between this heat in and out is going to be the Q stored. So, okay, no, actually I'm gonna stay here in the whiteboard. Okay. So, let's create a new whiteboard. So we write here our energy balance that was Q in minus Q out plus Q generated equals Q stored. We said there is no heat coming in, but we have heat out that is by convection. Typically, when we write this equation of convection, we say surface area times convection coefficient times Ts minus T infinity. But I didn't write Ts this time. I just wrote T. Anybody has thoughts about is just T and not Ts? All right, I'm gonna go for it. The reason it's T and not Ts is because surface temperature, core temperature, anywhere temperature is the same temperature. And so I don't need to say it's temperature at the surface, because it's just the same temperature everywhere. Q generated, if you remember, the table was 15.5 watts. I'm not gonna get into the causes of this heat generation, but I need to know it. And it's 15.5 watts. Q stored, and this goes back to week 1 of classes, was mass times the specific heat times the rate of temperature increase. In this equation I have here, I'm assuming there is no phase change because I'm using the specific heat. That means the change in energy with change in temperature. If I had a phase change, as it was the case of the freezing droplet in Snow Valley, is a different equation, which we also know how to handle. It's just not this case. This is the equation we have now. And if I put this inside here, I'm going to end up with minus Q out is minus AS H T minus T infinity plus Q generated, which is a constant, equals Isn't it interesting how we build from something so simple like these very simple energy balances and very simple heat transfer mechanisms? We ended up with a differential equation. Before we solve the differential equation, let's see what we might know so far. Let's do a graph of what we might know. And let's start with temperature versus time. So we know that we have a single independent variable. This is time is the independent variable. Temperature is our dependent variable. And we have a bunch of parameters that came up. And let's do the evolution. We know in the case of the problem, I remember this, we said we start at 30 degrees, C. Just imagining the computer was not completely cool to room temperature for whatever reason. It has transformers. This is a realistic number. The air surrounding this chip is at 20 degrees C. I have a question for you that I would like to read in the chat very quickly. When the chip is running, assuming lumped capacitance, assuming a surrounding temperature of 20 degrees C, that the air is at 20 degrees C, is this chip going to increase in temperature, decrease in temperature, or stay at the same temperature? I'd like to see some suggestion. Increase, decrease, or same? What do you think is going to happen before we solve any differential equation? Increase, decrease, same. I know we have enough people in logged in, so somebody, I'm sure, will have a take. Anybody with a computer? Oh gosh. Okay. I get a comment that the audio is spotty. Is it spotty for everybody or just for one? If it is spotty for everybody, then we might have a bigger problem. Okay, good. Well, somebody suggested the temperature is going to decrease. And this is consistent with what we had said before. Except when we talked at the case of the sphere had no heat generation. But the chip is generating heat. Actually, the whole point why we have these cooling fans and these cooling pins and these sophisticated cooling systems is because a chip goes up in temperature because it's generating heat. So very important. And most of you don't need to take the heat transfer class, know that when you turn on electrical equipment tends to get warmer. And we are going to tackle it with the same fundamentals we did before. But to cut a long story short, I know that since it gets hot, and it doesn't get hot forever, it's the evolution is going to be something like this. and we're going to have a steady state temperature. What is it? We're going to determine at what temperature the chip operates. All right, cool. So this is what it's going to look like. And I know this because I know when I start, I know that at some point the chip stops increasing in temperature because I know that typically the chips don't melt down. We're going to see what happens when they do. So I'm going to have a steady state temperature, and then I'm going to have a characteristic time. No math involved so far. The only thing we needed to know is that the chips in a computer tend to get warm. And I'm not going to be quizzing you on chips in the exam. It's only the heat transfer. I'm telling you now that they get warm. Okay, so we had our differential equation, and we're going to rewrite the equation. I'm going to rewrite our differential equation so it looks in the standard way. It's going to be dt. Or maybe my chip is melting down here. Okay. So if you guys are there, can somebody tell me if you're still getting me, because my Zoom somehow froze. And
Hey, we can hear you. It's just the picture is frozen.
I hope you guys are taking this more gracefully than I am, because I'm getting quite upset. Okay, but thank you. So let's see. I'll try my best. You guys can hear me. Thank you very much. And so I'll try to continue using the so okay, I think we're back home. All right, so let's see where we got. Gosh. Well, all right. Let's see how this goes. All right. Let's see. Anybody still out there? Like, no.
We can still hear you.
Okay, I am sorry about that. I have no idea what happened, but I had a major crash. So we have the last few minutes in the class. Let's do two things. One, I really would love for you to learn this stuff. It's all in the notes. I'll be here in the office hours, and I'll be handling emails for anybody who's curious and interested in learning more about heat, about lumped capacitance with heat generation. For the quiz on Wednesday, I'll go as far as I managed to explain, and not beyond. So I hope you'll read. I hope you'll learn it. I hope you're curious, and for the exam on Wednesday, we will cover up to the point in which the video crashed. I hope it was the recording was saved, and I will upload it for you. So if anybody has any questions or comments so far, we have a couple minutes to field them. And if not, I'm going to see all of you later on at the office hours.
Professor, what page was it that where you left off?
All right, so let's stop here then, and I'll see the office hours will start at 2 p.m. as usual. Yes. And I'll set up a different computer. I'm already in a different computer now. I'll set up a different computer to connect with you better. I'll see all of you interested at 2 p.m. Thank you.